Hi everybody, it's Mr. Lee, and we are here for probably the final video for this unit, this constant velocity particle motion or particle model unit. I'm calling this one velocity graphs analysis. Alright, so hopefully by now you've come across a couple of velocity time graphs, and this video is going to help you out with all the powerful things that you can do with a velocity time graph. Now for the physics course, the velocity time graph is one of the most common and useful graphs that we will see, and so it really does help to get a very nice in-depth analysis of what we can expect. So let's begin. The first thing I want to do is I want to create a velocity time graph, nice and easy. All right, this will be velocity meters per second, and of course down here will be times in seconds. Now for those of you with a discerning eye, you'll see that up here we have a positive region and down here we have a negative region, because velocity is a vector and direction matters. Now we can call the positive region to the right and negative region to the left, or forward and backwards, but whatever the case is, we need to have a positive and a negative region. All right, now next thing I'm going to do is I'm going to give you a little verbal. Hopefully by now we are used to doing verbals and you realize how powerful they are. So let's say, all right, if you traveled with a velocity of 6 meters per second for 5 seconds, how far did you travel? All right, so simple enough. Let's see if we could make this a little bit bigger. Yeah, let's do that, 20. All right, if you traveled with a velocity of 6 meters per second for 5 seconds, how far did you travel? So the first thing that I want to do is I want to show you the different ways that you can look at this problem based off of what we've done in class. So one of the first things that we did in class is we collected data, right? So we can do a position time graph chart. All right, so let's say we start at the origin. Time seconds always have units. At the 0 second, we were at the 0th meter. After 1 second, we traveled 6 meters. After 2 seconds, 12, 3, 18, 4, 24, and the final one, of course, is 5 seconds for a total of 30 meters. All right, so that's one way of looking at this. Another way to look at this is simply by just doing math, right? So if we traveled, or if we are moving at 6 meters per second, and we travel for 5 seconds, what you're seeing here is a little bit of unit math. So I'll use a different color ink to really showcase what I'm doing here. I have seconds here in the numerator and I have seconds here in the denominator, so they cancel out. So that leaves us with 6 meters times 5, which gives us a total of 30 meters. Okay. Another way that we did that is we used the definition of velocity, which is total displacement over the total amount of time. And we know that our velocity is 6 meters per second, and our displacement is what we're looking for, and we're looking for the time, which is 5 seconds. And so we rearrange our variables, so we get 6 meters per second times 5 seconds, and that just gives us, once again, 30 meters. All right, so if you're wondering, Mr. Lee, why are we just getting the same answer regardless of what we do? Well, that's what I'm trying to show you, right? There's a lot of different ways to get that answer. But the one way that we didn't use yet is by using this graph, all right? So if we take a look at this graph here, I want to make sure that the verbal matches the graph. So let's create a little mark right there that will represent our 6 meters per second, and we do have a constant velocity. I'll do that in a different color. Boy, that's not straight at all. Okay, there we go. Dotted lines are easier. All right, so we travel for 6 meters per second, and if you are wondering what about the time, right there, for 5 seconds. All right, so if we were to have a velocity time graph, we have a graph that looks something like this. A couple of very important things that I want to highlight, and let's do this in red. Here, this shows constant velocity, okay, which means that the velocity is not changing. it is a flat line. And we will come across scenarios where the velocity changes, but today's not that day. Okay, so how can we find our answer of 30 meters graphically? Well, let's take a look. The answer is a very useful mathematical tool, and we will do this a lot. It's called area under the curve. All right, I'm going to erase this a little bit there so that I can jot down some notes. So area under the curve. All right, so what that means is if you take a look at the graph here, okay, we see that we have a y-axis and an x-axis, and we have this line. So the technique that I'm about to show you is called the area under the curve technique, where you go from the line that you drew, okay, and you simply shade in that area up to the x-axis. So it will look something like this. Okay. Trust me when I say that the shading technique, it really does help. Now, to really hone in on a point, what I'm going to do is I'm going to put up a graph paper so that you can see exactly what I'm doing. All right, so in front of you, you should hopefully see the graph paper. All right, and the reason why I want to do the graph paper is because in class, more than likely, we'll be using the graph paper to really practice this technique, and I'm going to show you exactly what it looks like. So down here, I'm going to recreate our graph, okay? We have a velocity here. Let's see, this will be 1, 2, 3, 4, 5, 6. So this will be the 6 meters. So 1, 2, 3, 4, 5, 6. So this will be the 0th line. All right, and we move for 5 seconds. So this is 1, 2, 3, 4, 5th second right there. All right. Now we have a y-axis of that. Oops. T seconds velocity time. All right. Now let's recreate the line for the graph that we see right there. Okie dokie. And so now we're caught up with where we were before, but now with graph paper. Now, if you have graph paper at home, it really does help to recreate this. But if not, that's fine. You can see exactly what I'm talking about. So the area under the curve, if you remember, I said you go from the line that you created, okay, and then you try to create a shape to the x-axis, right? So in this case, I went from the velocity line, and I went straight down to the x-axis. Okay, and that's the key part. That's the part where a lot of students mess up. They don't know where to exactly go, and they might go a little too far. But your stopping point is the x-axis. And if you remember from the previous graph, okay, up here, I shaded in that shape. And in this case, I want to do the same thing, but with intent. So what I mean by that is I'm going to show you where we can find our answer of 30 meters per second. So if you take a look here, this is block 1, okay, that's 2, that's 3, that's 4, that's 5, okay, so that's 5 blocks, 6, 7, 8, 9, 10 blocks, 11, 12, 13, 14, 15 blocks, 16, 17, 18, 19, 20 blocks, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30 blocks. All right, so you can see that from the shape, we have a total of 30 blocks. Now, we're going to get a little bit more into the math behind why this works. So what I essentially found is the area. Okay, and the area in this case represents the 30, right? So if I were to say here, this is 30 blocks. The area in this case represents the displacement. And the area for this shape, and I want to emphasize that you're trying to find the area of the shape, is it's going to call it a rectangle. This is a rectangle. So the area of the rectangle is the base times the height. Okay, so that line is probably the most important line for this entire video, right there. The base, in this case, the variable for this base is time, and the height variable in this case was velocity. And we know that this area, this rectangle, represents our displacement. Now, here's what's really cool. If you see this definition right here, we said that the displacement is equal to times the velocity. We could just rearrange it to something that we're used to. right? The displacement is equal to the velocity times the time. And I'm going to highlight where we saw that before. Let's do a different color. Let's do blue. All right. So here we have displacement, and if you take a look up here, that was the same formula that we use up there based off of what we did from our first definition of velocity, right? It's just a rearranging of the variables. So here's a couple of key takeaways. One, what do we call this, right? So this is what we call the general math representation, which is just a really fancy way of saying what do we do with the graph mathematically. Okay, so that's a general math representation. So if you're wondering, when I ask you what is a general math representation, all I'm asking is, based off of the graph, what did you do mathematically? Okay, now from here we found that the displacement is equal to the velocity times the time, and we got that by looking at the graph and seeing that if we traveled for 6 meters for 5 seconds, we traveled for a total of 30 blocks, right? And then we said that those blocks represents this area, and the area was this area for a rectangle. Now, here's what's really cool about this, okay? This right here is the final wrap up in the constant velocity model. Okay, and this is what we basically did for the buggy lab, right? We had a buggy that moved for a constant velocity, and that buggy traveled for a certain amount of time. And based off of that, we can now find the total displacement that that buggy traveled. Is that really cool? All right. Now, in the future, you'll see different kinds of graphs where I'll ask you to use the area under the curve technique. And so, here's a little shortcut, and I'll remind you this as we go along. In your formula, okay, if you have, or if you're wondering, where do I use the area technique versus the slope technique? Area is when you multiply the x-axis versus the y-axis. Okay, the x-axis times the y-axis. All right, so in your formula, if you ever do that, you're looking for the area under the curve, and we can see that right there, right? Velocity times time. We use the slope technique when the two variables are being divided. Okay, and in this case, slope is a rise, which is the y-axis, over a run, which is the x. And we saw that when we did velocity is equal to displacement over time, right? So you see how those two variables are being divided. That means we use the slope. For this case, we said displacement is equal to velocity times time. You see that right there? That shows us that when we are multiplying the x and the y-axis, we use the area. All right, now I'm gonna start this. One of the most important techniques that we can use all year. Please commit this one to memory. All right, the only other thing that I want to really show you is when I say sometimes students have a hard time really finding the area under the curve. Let me show you exactly what I mean. So far we saw a positive area there, right? We saw something that looks like this, but what if, right? What if this graph just jumps down here? So in this case, a variable could be, so for here, let's say for this part, a car moves with velocity 1, 2, 3. Let's say 3 meters per second, positive. Okay, and then here, okay, car turns around and moves with velocity -2 meters per second, and I'm gonna put that to the left. All right, so in a scenario like this, find the area on the curve. It could be a little tricky, but let me show you exactly how it's done. So I'm going to use a highlighter to really showcase how to find the area on the curve. And I do suggest if you have a highlighter at home, once you get used to it, the highlighter really does help in finding the area on the curve. All right, so the positive one, the area is pretty simple, right? So that's the shape right there. If you remember our rules, we have to go from the line, okay, and we have to create the shape to the x-axis, and that shape is this square that I outlined right there. Okay. Now for the second part, the rules are the same. You go from the line, and you try to create a shape from the line to the x-axis. Okay, and notice that here's the x-axis. It's above the line. So the shape that you'll create will look something like that. And I'll do this in red. There we go. Look at that. So an important thing to know here we have positive displacement. Okay, because displacement is velocity times time, and here we have a positive velocity, but here our displacement will be a negative displacement, and the reasoning is displacement is velocity times time, and here down below we have a negative velocity. So negative velocity will give us a negative displacement. Okay, all right, that's that. I'll see you next time. Bye bye.